So in this video, I'm going to go over this example. This is the differential equation that's given to us. It's y double prime plus 2y prime plus y equals 0. The first solution that we're given is y sub 1 equals x e to the minus x. And we are going to use the reduction of order method to find a second solution to this differential equation. The reduction of order method says that we're going to find a second solution, y sub 2, which we're just going to call y for simplicity. So the second solution that we're going to look for, we're going to label it y, is equal to y sub 1 times the integral of y sub 1 squared over e to the negative integral of p of x dx, and this is dx. P of x, when the equation is in standard form, is going to be the term in front of the y prime term, whenever this is a second order linear differential equation. So this is p of x, it's just 2. And y sub 1 is the solution that's given to us, which is x times e to the minus x. So when we plug this in, we're going to have x times e to the minus x times the integral x e to the minus x, x e to the minus x squared. That's a little bit funky, but it's okay. The numerator is e to the minus integral of 2 dx. So this is going to equal x times e to the minus x. The integral of x times e to the minus x times e to the minus x is x squared, and then e to the minus x times e to the minus x is e to the minus x plus minus x for the numerator. So it's going to be e to the minus 2x. And then the numerator is going to be e to the, and the 2 is going to come to the front of the integral, so it's going to be e to the minus 2x. And this is also an integral, so this is going to be dx. But then the e to the minus 2x will cancel out, so the integral is simply going to be x times e to the minus x, the integral of x to the minus 2 dx, which is going to equal x times e to the minus x. X to the negative 2 integrated is going to be x to the negative 2 plus 1 divided by negative 2 plus 1. So it's simply going to be negative 1 over x plus some constant c. So the x's cancel out, and we're simply left with e to the minus x plus c. And because we used the shortcut formula, this, I'm trying to pick a blue ink here. This is y sub 2. Y sub 1 is already given to us, x times e to the minus x. And so we can now form a general solution of this differential equation with these two solutions. But the instructions simply told us to find the second solution, which we did. And we can also verify that these two functions are linearly independent, and therefore they form a fundamental set of solutions to this differential equation using the Wronskian. And I'll go ahead and do that now, just so that we have it on. That's just a good habit to have, of using the Wronskian to verify that the two functions that you found are linearly independent. So the first function is x times e to the minus x. The second function is e to the minus x. The Wronskian is a determinant, so it's going to have to be a square matrix. The first function is x times e to the minus x. The chain rule of this derivative is going to be e to the minus x plus x times the derivative of e to the minus x, which is simply minus e to the minus x. So I'm going to erase this, write the negative e to the minus x. And then we have the second function, e to the minus x, and its derivative is minus e to the minus x. Then we multiply and subtract that multiplication there. So we have x e to the minus x times minus e to the minus x minus e to the minus x times e to the minus x minus x e to the minus x. And then we're going to multiply all that out. So these two terms here, and then this term with this term, but then we have to remember that we have this multiplication sign here, which is going to affect everything. So let's go with the first term here. It's going to cancel, these two minus signs are going to cancel out. So this becomes a positive, and this becomes a positive right there, because those two are going to cancel out, those two negative signs. So x times e to the minus x times e to the minus x, those two are going to add together, so it's going to be e to the minus 2x. And then we have minus, and let's put this in parentheses, e to the minus x times e to the minus x is going to be e to the minus 2x minus x times e to the minus 2x. And then this minus sign is going to distribute out to these two terms here. So we're going to have x e to the minus 2x minus e to the minus 2x plus x e to the minus 2x. And so these two are going to add together. So it's going to be 2x e to the minus 2x minus e to the minus 2x, which does not equal 0. Hence, the functions form a fundamental set of solutions on negative infinity to positive infinity, but there was no interval given on this equation, so technically the instructions don't really ask us to verify that. I just did it because I want to include that also in my example here of using the Wronskian to verify linear independence, even though this video isn't really about that, but might as well just include it on there just for good measure. So I'm going to check on Chegg to see if this is the correct answer. I'm pretty sure it is, but even I make mistakes. No, I'm just playing. That makes it sound really conceited, but I make a lot of mistakes. Make a lot of mistakes in my work, and so even when I get to the answer, sometimes I like to check it. Most of the time I like to check it just to make sure that I got the right answer, and I did make a mistake. So the second solution of the given differential equation is minus e to the minus x. Let's see if I can find my mistake here. Let's check and see if the given differential equation is correct. That's all correct. Y sub 1 x e to the minus x. Okay. So let's check and see if my formula is correct. Y sub 1 times the integral e to the minus integral px dx over y sub 1 squared dx. X e to the minus x. And that's in standard form. So that's minus 2x. Did I get that correct? X squared e to the minus x. That's x squared. It's e to the minus 2x. Those cancel out. And so it's x e to the minus x times the integral of x to the minus 2, which is x to the minus 1 over minus 1, which is negative. Yeah, that's what it was. I didn't put the minus sign there. The minus sign was right here, and I forgot to include that in the final answer. So that means that this entire Wronskian would have been different had I included that minus x in there. But for the sake of time, I'm not going to redo that because, number one, the problem doesn't ask for it, and number two, it's simply going to make the one of the terms cancel out, and it's simply going to be not equal to 0. And that's the ultimate goal of the Wronskian, is to determine whether or not it's equal to 0. And if it is equal to 0, then that means they are linearly dependent and they do not form a fundamental set of solutions. If it is not equal to 0, that means that they are linearly independent and that the functions do form a fundamental set of solutions. So thank you for watching. If you made it this far, I'm going to go do some more examples and make this process smoother as I go along. Have a good night.